With over 2 decades of experience, he has worked in key roles at Fermilab, Xilinx, and Intel, focusing on RF cavity design and superconducting qubit system. For today's workshop, Dr. Awida will present on design of superconducting quantum chips and introduction from future innovators. So without further delay, Dr. Muhammad, you can take it over.
Yeah, thanks, Alex, for the intro. It's a pleasure to be with you today in this great workshop. It's exciting time for quantum. In today's talk, I will tell you about how do we design superconducting quantum chips, and I will give an intro on the design of both qubits, quantum amplifiers, and in general also, we'll touch on quantum system design. So I kind of divided the talks into 4 pieces. The first piece is just an intro in general for quantum computing, and I will try quickly to go over the big question, like why we are interested in quantum computing, how we do quantum computing, and when we will realize a quantum computer, and those kind of questions that I call them the big questions, right? Next, I will narrow down to superconducting quantum systems, and I will give an introduction. We'll talk about the major components like Josephson junctions, quantum devices, qubits, resonators, quantum amplifiers. Then I will drill down and take a closer look at designing qubits, designing quantum amplifiers, and then the designing challenges there. Then we'll briefly talk about how EDA or electronic design automation tools can help navigate those challenges. And I will talk specifically about 2 solutions that Keysight launched specifically for enabling quantum design. So without further ado, let's talk about quantum computing. Why people interested in quantum computing, and what is the big deal? So in very quick way to to address this, it's this exponential growth in computing power with the number of qubits. In other words, if you have any qubits, they are equivalent to 2 to the n bits. Of course, this without talking about error correction and things like this, but this exponential growth is what is fascinating about quantum computing, because it will give us a computational power far exceeding anything that humanity knows so far. And the other thing also, it does address real life problems. Take, for instance, the traveling salesman problem that I'm highlighting here to the left, where a salesman is traveling between too many stops and trying to optimize the path between these many stops. The problem is NP hard, or it's not tractable on classical computers. As the number of stops increase, at some point you will not be able to solve it exactly on a classical computer. But then it's very manageable on a quantum computer. And this is an example for an optimization problem that many industries could benefit from chemicals, pharma, finance, aerospace, automotive. So almost every single industry will be impacted by a quantum computer when we have it. And Times Magazine listed 9 ways quantum computing will change everything, from safer aeroplanes to discovering distant planets, to boosting GDP, to detecting cancer, and so on and so forth. On the other hand, also quantum computing will be disruptive because it will change the encryption, because a quantum computer will be able to break the RSA code that we currently using, so which basically says that we have to move from the current encryption that everybody's using to a new post-quantum encryption method. Now, the next big question is how quantum computing is implemented, or what is the two main principles behind quantum computing. So I call them two of them are really important to understand and have a good handle of. Quantum superposition and quantum entanglement. Superposition is that when you flip a coin, you have either head or tail. That's the bits, the classical bits, 0 or 1. But a quantum bit or a qubit is actually as if it's a rotating coin, and it's in a simultaneous superposition of head and tail. So that's why we say a qubit can be in 0 and 1 simultaneously. Until you measure, it will collapse to either 0 or 1. Now, if you take this two coins and you started with them being entangled together, and Alice and Bob, Alice has a coin, Bob has a coin, they travel very large distance, and then one of them measure his coin, there is a correlation, and Bob can know what his coin will be through this quantum entanglement that spoke actually Einstein say. So he called it the spooky action at a distance. Now, if we have n qubits, in order to get this 2 to the n exponential growth, we got to put all the qubits in entanglement. And that's why we talk about superposition and entanglement hand in hand. Now, in general, what do we need to do to build a quantum computer? You need an entity, an object that can be a quantum object, whether it's an atom, electron, or photon, you name it. But you need a quantum object. You need a readout for that quantum object. So quantum physics tells us that you cannot infer directly the state of the atom. So you got to have this readout system to indirectly infer the state of the atom. And then the cavity will get affected by the state of the atom. It will change, for instance, one of the examples that it will change its frequency. So you will be able to tell if the atom in ground state or excited state through the frequency of the cavity. And then you prepare the atom, let it evolve over time. And that's actually the quantum computing happening through the atom evolution over time. And then eventually, after the atom evolve over time, you indirectly read the state through the cavity. So that's kind of, in a nutshell, what do we need to do in order to make a quantum computer. Da Vincenzo put his famous criteria, eventually we want to scale the quantum computer and build a bigger one. So in order to have a path towards this universal quantum computer, we got to satisfy the criteria, which is being able to scale the number of qubits, being able to initialize them, having a decent coherence time for the qubit so that it's enough to, let the atom evolve over time and do useful operations during that time. And then we need a universal set of quantum gates. We need to have a qubit-specific measurements in order to, at the end, you want to measure the state of the atom, and that's the measurement part. So this 5 criteria fulfills what do we need to have to realize a quantum computation. And there are 2 other criteria for quantum communication, flying qubits, and faithfully transmitting the flying qubits. Now, we have so many technologies, right, for quantum computing. We just said we need an atom. This atom could be natural atom, like, for instance, cold atoms, they use natural atoms. Could be photons, could be electrons. So through the spin of the electrons, you realize this quantum object that you need to have a quantum computer, or could be also artificial atom, like the man-made atoms that we will talk about for superconducting qubits. So that sums up the big questions. Oh no, there is one remaining. So when will we realize quantum computer? The answer here is that right now we have a scale of hundreds of qubits. Experimental quantum advantage already demonstrated. But we have its challenges, right? We need to make better qubits in terms of fidelity and coherence time so that we do better in error correction. So we do also need advanced techniques for error correction and reduce the overhead of error correction. And we need to be able to scale the quantum hardware, scaling the number of qubits. So this three fronts really sums up where we're standing right now. So people, the quantum ecosystem investing lots of energy to scale the number of qubits, to improve the qubit fidelity and coherence time, and also to realize error correction. Once we have this, then next step would be building a universal quantum computer. So near term, we'll have quantum computers solving specific niche problems like optimization, for instance, or quantum chemistry. Long term, we'll have general purpose quantum computer once we have error correction in place. So this sums up the first part of my talk about an intro in general to quantum computing. Then I will drill down now on superconducting quantum systems. So I'm bringing back this picture of the different hardware, and the focus of my talk today is on superconducting qubits. In that sense, superconducting quantum systems, if we try to make a cartoon for such a system. So on the left, on the right here, I have a cartoon of a dilution fridge where this dilution fridge goes to ultra low temperature, specifically to combat noise. Noise is a big deal, right, for quantum system. So when we go cold, the noise gets suppressed, and we have here the heart of the system, the quantum processing unit, at the ultra low temperatures stage. And then we have a bunch of attenuation on the input lines to suppress room temperature thermal noise. And then at the output, the signal, when we deal with quantum systems, we operating very near from the noise floor. So the output here is nearby the noise floor. So you do need to do quite a bit of amplification in order to, improve the chances of reading the signal with good fidelity. So you do need a quantum amplifier at the output of the quantum processing unit, then a bunch of other amplification stages on the output. And if we were now to list the components of the system, the major components. So we have the quantum processing units, and that's, as we said, this is the heart of the system. We have the quantum amplifier, which is very, very important to improve the fidelity, the readout fidelity. And then we have the overall cryogenic system that contains all these components that we need to take account of. Now I will give a bit of basics to entertain, give a foundation for how do we design superconducting quantum systems. The first piece, and it's very critical, is the Josephson junction. So the Josephson junction is a tri-layer junction, superconducting insulating superconductor, and then the insulator here is very thin, like nanometer scales, and you get copper pairs tunneling through the insulator, and you have the supercurrent. So Josephson discovered this in the 1970. He got Nobel Prize. And the way from engineering perspective to think about a Josephson junction, it's a nonlinear inductance. And this nonlinear inductance, as we will see next, enables us to build an artificial atom. So Josephson junction is really, really super critical for superconducting quantum systems. We use it to make qubits. We use it to design quantum amplifiers. And as I said, it's like, more or less like a transistor for classical electronics. That's the same rule here for the Josephson junction. Now, sorry, I got backward. So we said that the Josephson junction is a nonlinear inductance, and it enables us to realize the artificial atom. When people talk about artificial atom, what do they mean by this? That you have two-level systems that you can address. Meaning, if I have this two-level system and I have a photon at the zero level, if I put energy equal to omega 01, the photon will get excited from 0 to 1. So the artificial atom will get from 0 to 1. And now it will stop, will not go from 1 to 2. Why? Because omega 01, the transition from 0 to 1, is different from 1 to 2. And that's what we call anharmonic oscillator. Anharmonic oscillator means that you have omega 1, 2 different than omega 01 and also the other transitions as well. While if you have a harmonic oscillator, they are equidistant. So omega 01 equal to omega 1, 2, omega 2, 3, and so on and so forth. So if there is a photon here and you got energy that transition you from 0 to 1, it will keep going. I mean, there is nothing will stop the atom from evolving across various energy levels. And this is not useful for quantum. So harmonic oscillator will not be useful to make a qubit. So you do need nonlinearity in the system. The nonlinearity enables making this transition different between 0, 1, 1, 2, and so on and so forth. So to sum it up, Josephson junction rule here is, as a nonlinear inductance, is to make an harmonic oscillator, and then the anharmonic oscillator makes the artificial atom, the one that we can address it as two-level system. So you have a ground, a distinct ground and excited state. And then from the Josephson junction, we build all the fun quantum devices. So we can build the JJ itself. I mean, the JJ can stand by itself, but you could also make squids like superconducting quantum interference devices, like any loop of superconducting will have its own manifestation of flux quantization and so on and so forth. If you have a JJ alone in a loop, that makes an RF squid. If you have two JJs, makes a DC squid. And then each one of them is useful for quantum in various ways. So you could tune, for instance, a qubit if you have a squid in it, and so on and so forth. Also, I'm flashing here the various types of qubits, like a charge qubit, flux qubit, phase qubit. And the difference here is that how we encode the information. So the information here is coded in the charge states, here is coded in the flux, and here is coded in the phase. We will come to realize in the coming slide that, for instance, transmon is a charge qubit. That's one of the mainstream qubit at the moment. So transmon is being used across the board by various, hardware quantum hardware providers at the moment. We kind of, years ago, we started from a copper pair, but then we evolved it to a transmon. Both of them are charged, but copper pair box is prone to charge noise. With the transmon, we resolved this issue. We make it immune to charge noise, and now we get a decent anharmonicity, and then that's why the transmon is a mainstream qubit at the moment. There is also, ongoing work for fluxonium, where you can even make the anharmonicity larger, which enables also certain advantages, like improving the fidelity of the readout of the qubit. Now we'll also classify qubits by geometry. So you have planar qubits, which means what? Means that you have a wafer and you're printing the qubits, the resonators, everything on the same wafer. And that's where people scaling the number of qubits. At the moment, people build quantum chips with hundreds of qubits with this planar qubit approach. There are also ongoing work for 3D qubits, where now you have a qubit printed on a wafer, but then being enclosed in a 3D cavity. This also has its own advantages. So for instance, here you could improve quite a bit photon lifetime, because a 3D cavity will have lower losses. On the flip side, scalability is not as easy as how we handle it with planar qubits. Now, I also wanted to flash few microwave foundation before we build on it. So I will talk about microwave structures for quantum systems. So waveguides is really important, because, for instance, here, this 3D qubit is enclosed in a cavity. How do you make a cavity? You got to understand the modes and mode structure and so on and so forth. So understanding microwave waveguides is important for 3D qubits. So a waveguide is a structure that guides electromagnetic waves. It's from microwave engineering. It's well known, the engineering of it, but using it for quantum, that's where. So if you are a quantum physicist, you got to understand also microwave engineering here and the foundation for it. So typically rectangular waveguide, circular waveguide, the modes here. I'm not going to drill in the details, but I'm flashing that, for instance, rectangular waveguide, the mode structure has this distribution. The fundamental mode is T10. The circular waveguide, the mode structure is different, and then the fundamental mode is TE11. Next step is, from that waveguide, you make a cavity by enclosing the ends of the waveguide. Now you have a cavity. The mode structure will change. Now you have 3 indices, because you have 3 dimensions, and each dimension of them determines the resonant frequencies that will build up inside the cavity. It's very also important to understand how the quality factor is playing here. The quality factor of the cavity is a measure of how effective, describe how effectively the cavity stores energy, and also the higher the Q, it means that lower losses in the system, and then eventually better photon lifetime. So that's the connection to quantum. So that's for 3D qubits. Now for planar qubits, you're actually using a different transmission line or waveguide. You're using coplanar waveguide, where you have a wafer, you're printing a signal conductor here, and then you have ground around the signal. It's a well-known microwave structure being used for microwave circuits. And the advantages here for coplanar waveguide versus, for instance, microstrip line. Notice the difference here, that here you have a signal and then the ground in the bottom of the wafer, while here you have the ground beside the signal on the 2 sides. So coplanar waveguide is better than microstrip in terms of radiation. It has reduced radiation loss, which also means we'll have less crosstalk, because how we engineer the geometry. So that's why coplanar waveguides are the mainstream structure being used for quantum. Why? Because they secure less leakage for across the quantum chip, and also will support lower losses at high frequencies. One of the challenges when designing coplanar waveguides that you have actually, this is a desired mode. We call it the even mode, where the electric field is pointing outward from the signal to the ground. You have also a parasitic mode. We call it the odd mode. In this case, the field is pointing in the same direction. So for quantum, in order to get rid of the odd mode, we got to put air bridges or yeah, what do we call the other one? Air bridges or bond wires. So when we engineer a quantum chip in order to get rid of the odd mode, which represent a parasitic for the working mode that we want, it's very critical to put bond wires between the signal and the ground to make sure that you have between the two grounds, so that you have one ground across the chip. I hope that you guys paying attention to these details, because in terms of engineering, it's very, very important. Also, we'll flash a little bit of an intro to parametric amplification that we will talk about when we take a closer look at quantum amplifiers. So in this analogy here that I'm putting for how when people swing on a swing, how do they get the swing moving? It's actually they are using parametric amplification. So when you consider a person driving the swing during 1/2 cycle left to right of the swing, the person makes a full cycle up, down, up, and then this is actually the essence of parametric amplification. So the movement up and down is what bumping the swing. So the energy transfer from the vertical movement of the person standing and sitting to the swing, swinging left to right. So, and here, that's the synchronization of the movement and so on and so forth is very important to get the swing moving properly. And that's in principle exactly how parametric amplification also is happening for quantum amplifiers. Okay, so next I will talk about, we'll take a closer look at superconducting quantum systems, especially qubits, and we'll also touch on quantum amplifiers. So let's take a look at this single qubit, single readout chip. It's very simple. Again, you have here's a coplanar waveguide making a resonator with this gap here and this gap here. That's what will trap the microwave energy in the resonator. Pay attention also to the bridges, just to kill the odd mode that we talked about. Now you have a transmon qubit with the JJ in the middle, the Josephson junction. Again, this is a transmon pocket. The JJ rule here to make an artificial atom. So you have a qubit and a readout. We indirectly reading the state of the qubit through the resonator frequency in the sense that if the qubit moves from ground to excited state, it affects the resonance frequency of the resonator, so you will see a change in frequency. But how do we engineer such a system? We do need to find the frequencies of the qubit, the resonator. We do need to find the coupling between the qubit and the resonator, also between the resonator and the outside world. Like, you have a 50 ohm port at the in and out. So this also needs engineering. And the coupling here will determine what we will talk about in a little bit, the quantum parameters, unharmonicities, the cross-curve, and so on and so forth. Also, after this qubit, you do need a readout system, including a quantum amplifier, and that's talks about the full picture of designing and reading the state of that qubit. Okay, We'll also talk about quantum parameter extraction. So here we will model such a qubit and a readout with it needs it needs layout, it needs EM, electromagnetic simulation, so that you find the resonance frequencies and so on and so forth. There are two ways of actually modeling. You could drive the ports with signal, or you could model with eigenmode simulation, finding the resonance frequencies of the system. And this sums up to the two extraction techniques. One based on frequency domain. So from the ports, you find the S parameters, and then from the S parameters, you find the admittance, and then from the imaginary part, you find the zero crossings. And then from there, you can find the quantum parameters upon the change with the qubit inductance incorporated in the system or not incorporated. So that change in frequency with the qubit on and off will help you to find the quantum parameters. Another way is through eigenmodes, or people, in the there are also terminology here. So microwave engineers will use eigenmodes term for the simulation. Quantum people will use the term of energy participation analysis. But anyway, it's same thing. You find the eigenmodes, and then you find the field distribution, and then you find the participation ratios, which represent how much of energy each mode has in each qubit. And then from there, you can extract the quantum parameters. Of course, there are these two well-known techniques, very well-known in the literature. So you could visit these two papers for the details. But how do we really do it in engineering? It's I would say now it's quite straightforward. So you do models the problem with EM simulation, and then you find the solution, whether it's eigenmode or driven solution with excitation, and then we find the frequencies of the qubit and the resonator. We find the unharmonicity. The unharmonicity represent how far is the qubit departing from a linear system. It tells us the difference between GE and EF. This is the higher level transitions of the qubit. And that unharmonicity is also very well connected to the layout, because the capacitance that the qubit sees determines also this unharmonicity. On the other side, on the other hand, the cross curve, this off-diagonal term, tells us how strong the coupling between the qubit and the resonator, and this will affect how good is our ability in reading the state of the qubit. Because if these two frequencies are not separated well enough, there will be quite a bit of overlap between 0 and 1 states, and there will be quite a bit of error. On the other hand, you don't want to also make it too strong, because it represents a channel where the qubit could lose leak to the outside world if you make it very strong to the resonator. And also, it comes into play here the quality factor of the resonance frequencies of the qubit, of the resonator, which also translate to the photon lifetime, as we touched on earlier. So there is very strong design connection here to the layout. The capacitance determines the unharmonicity. The capacitance, the coupling also between the qubit and the resonator determines the cross curve. The quality factor of the resonance frequency determines the photon lifetime. So the workflow for superconducting qubits will look like this. You start from a schematic, you generate a layout, you solve the EM problem, meaning you model it, solving Maxwell equations and so on and so forth. Numerical techniques here comes into play, like finite element method of moment, and so on and so forth. Once you have the EM solution, you do a bit of post-processing to find the quantum parameters using the energy participation ratio or the black box quantization, or eigenmode and frequency domain solutions. Yeah, let's now switch gear to quantum amplifiers. So we touched on the parametric amplification and the need for quantum amplifiers at the output of the qubits in order to amplify the readout signal and improve the fidelity. But how does a quantum amplifier works? With the analogy to the swing, you have actually a bump signal that has quite a bit of energy, and this bump, the energy of this bump gets transferred to the signal, amplifying it through the nonlinearity of Josephson junction for quantum amplifiers. So we do need, in this scenario, nonlinear circuit simulation in order to model the nonlinearity of the system and get the mixing products and so on and so forth. This is an example of a J-tuba, a Josephson traveling wave parametric amplifier, where you have many Josephson junction loading coplanar waveguide, and then also you have a resonator loading the coplanar waveguide. So it's a chain of Josephson junction, and then it's a traveling wave structure versus resonant structure. So it's actually the signal travels, does not get trapped inside the transmission line. And then you have very long structure, so it's consisting of hundreds of supercells. And then with the fact that it's non-resonant, it comes the advantage that it's wide bandwidth. If you were to do a single Josephson junction device, you end up with a narrow bandwidth because it becomes a resonant structure. But then on the flip side, the design and fabrication here is really complicated. Think about this: how complex is this layout, and how complex will be the modeling of such a device. Now, to sum up the design challenges of superconducting systems, what do we see so far? So we see qubits, and the need to scale the number of qubits to hundreds of and even thousands of qubits. And then the path to do this, that you will need to do multi-layer chip. So the qubits will be on a layer, the resonator, the readout resonator in another layer, the input lines on another layer. That's because, simply there is no real estate on a single layer to accommodate all of this for a single wafer. So the future, actually, IBM, for instance, already doing multi-layer quantum chips. But then, with the need to go for larger chips comes also the challenge of how to model such a large electrical system, how to model the crosstalk, and so on and so forth. Plus the typical challenges here of having coplanar waveguide with very minute features. So we're talking about micrometer scale feature versus the chip size tens of millimeter. And then quantum amplifier, also same scenario. So you have, for instance, this Josephson traveling wave parametric amplifier with very large structure and also same minute coplanar waveguide features, complex layout, electrically large crosstalk. So this four challenges really sums up the modeling bottlenecks for both qubits and quantum amplifiers. And then just again showing the cartoon of the dilution fridge, and then the specifics here for the qubits and the quantum amplifiers, and how we scale to make large J-tube as with many Josephson junction. And then again, iterating as the fact that Josephson junction is a building block for both qubits and quantum amplifiers. Now, finally, we'll tell you about EDA solutions that Keysight provide as of today to enable people and designers to navigate those challenges that we talked about. So Keysight is well known for test and measurement equipment, including specific solutions for quantum, like the quantum control solution. But we do also provide electronic design automation tools. We have a flagship product that's EDS, Advanced Design System, and it's well known in the microwave circuit market. For quantum, we think about quantum computers evolving and design for them like how cell phones evolved over time. So now the engineering of cell phones and the design and then the design cycle, the workflow is well mature. You have a specific solution that enable doing RF board simulation, system level simulation, antenna, device modeling, RFICs, and so on and so forth. Quantum computers on that path as well, although it's very early in the past, but eventually the engineering of quantum computers will move from being a science to just engineering, like how cell phones evolved over time. Here we always say we go where the signals goes. Here we will also go where the photons go with quantum amplifier design, qubit design, system design, device modeling, and noise analysis. For superconducting quantum systems, actually, if we look under the hood, the qubits are coplanar waveguide resonance circuits, so it's well-known microwave problem, the engineering for it. I mean, the foundation for engineering coplanar waveguides is well-known for 30 years or so now. Quantum amplifiers also is nonlinear parametric microwave circuits, and this kind of parametric circuits also well known, the engineering for it for quite a bit of time. And the twist of using it for quantum and then the specifics of how to engineer those systems for quantum needs is what is need to be evolve a little bit more. And in that sense, we see that the themes for electronic design automation will evolve around 4 themes. So layout, that's the beginning. You do need to have a quick way of building your quantum chip, whether it's a qubit or a quantum amplifier, you name it. So, and this is should be straightforward to do. Now, we do need an EM solution that enables scaling the number of qubits, extracting quantum parameters for large circuits, and we paying attention to this part as well. And then for quantum circuits, we do need a solution that can take into account the manifestation of quantum circuits in terms of flux quantization and tackling very large circuits consisting of 1,000 Josephson junction. As of today, we do have solution at Keysight specific to quantum layout and quantum pro for EM, and then quantum circuit SIM for quantum circuits. We have also in mind that eventually we want a system solution that enable people to virtually test bench their experiment without the need to, actually cool down and warm up and change things. And so you will be able to iterate on your experimental setup with an EDA tool, which will be great. So some point in my life, I was running a dilution fridge, and I know the pain of, cooling down and then finding that something is not working properly because we installed the wrong, I don't know, filter or whatever. So, and this is something that we working is in our roadmap at Keysight. So Quantum Pro, we released it last year with quantum, with superconducting qubits in mind as a solution that can take you from end to end, from layout, electromagnetic, EM simulation, quantum parameter extraction, and nonlinear circuit simulation. This is an example for a 4 qubits and how we do the extraction here for the Hamiltonian of the system. Bringing back the workflow that we talked about. So we did have this workflow in mind. So we have a library of components that enable you to build your circuit, and then your layout gets generated from the schematic. Then your EM gets generated also from the, with a push of button, you are in the EM flow where you can solve the circuit with multiple numerical techniques, include the superconducting material, the kinetic inductance into account, and then extracting the quantum parameters. We also, evolving over time, adding more features. So we did add multi-layer technology to enable scaling the number of qubits. A year ago, 6 months ago, we added layout for JTuba to enable people building their JTuba in EDS. A couple months ago, we released Quantum Circuit Sim with the feature of flux quantization in frequency domain, so that people can build their circuit and model it in frequency domain, taking it into account flux quantization. I'm not going to drill in the details, but just flashing that the solution, we're listening to the quantum ecosystem and what people need to do to, take their design to the next step. So one of the requests that we got was flux quantization in frequency domain, and we very excited to have it now in EDS. This is another example for designing JTubas in the circuit environment, uniform JTuba, flow-K JTuba, and then what it takes to model JTubas consisting of thousands of Josephson junctions. Here also, I want you to pay attention to this slide because it shows how would you connect the EM flow to the circuit flow to take into account the nonlinearity of the Josephson junction. So the EM flow is linear, is completely linear. You abstract the qubit by its corresponding inductance. You model it that way. But what if you want to see the power dependence of the chip? In this case, you do need to get the response of the circuit from the EM flow incorporated in the circuit flow, and then through the Josephson junction model, that's how you get the nonlinearity. You could also, you will need also to do harmonic balance simulation to take into account to see the power dependence of the response of the circuit. So for instance, here what I'm plotting is the response of the resonator versus power. And then guess what is happening here? When you increase the power level, nonlinear bending starts to kick in because of the nonlinearity of the Josephson junction, mimicking exactly how we bring up the system when we do initial cool down with the network analyzer, where you sweep the power level of the excitation with the network analyzer and check that the qubit is live by witnessing a change in the response of the resonator. So it's very, very powerful to be able to do this also with EDA tools. Finally, flashing here that we know that quantum ecosystem likes Python and Python automation. So we do have this also in our tools to enable automating the workflow and so on and so forth. And I think this is my last slide. So flashing few resources. I invite you to visit the Quantum EDA page at Keysight. For student resources, please go to this page where you will find details about how to get a license and further resources specific to students. If you have issues or you want to talk about educational license, please email this email. And then there are a bunch of examples inside EDS in the design flow examples for designing simple qubits like single qubit, 4 qubits, also simple amplifiers, quantum amplifiers for like Josephson parametric amplifier. So basically, if you get EDS, if you open the examples and go to quantum design flow examples, you will see a bunch of examples that can get you started and could be also a good exercise to do, and you know, a challenge to do, because you know, I know that you guys want to also do a bit of challenge here. So feel free to explore the design flow examples, and then further details about how we do quantum extraction in the app note, and that's it. So in conclusion, you know, we well aware that quantum computing is a pivotal inflection point in computational technology. Very excited to see this exponential scaling and this fault-tolerant quantum computer happening. But in order for this fault-tolerant quantum computer to happen, we do need a bunch of engineers and researchers to make the move towards fault-tolerant quantum chips by scaling number of qubits, by improving fidelity, and by also improving coherence time. Those systems are quite complex, and engineering is quite a bit of a feat here. So modeling such systems requires you know, intensive engineering effort in order to model large scale qubits, or larger scale also quantum amplifiers. And that's it. Thanks for listening, and time for questions.
Yes, thank you very much, Dr. Mohammed, for this great talk. Yeah, we do have some few questions. I will just go and forward it to you. Okay, the first question is about how do bond wires contribute to the elimination of the parasitic odd mode of transmission?
Yeah, so think about it. Once you have a single ground, there is no place for the odd mode to propagate. You suppress the odd mode, and then it's only allowed, the only mode that will be allowed is even mode. So that's in essence what is happening once you have the bond wire connecting the grounds. The electric field will not be able to point that way, same way for the odd mode. It will have to be that way. But provided that you put the bond wire, you know, often, you cannot put just one towards the ends, for instance. You got to put them every now and then along the transmission path of the coplanar waveguide.
Okay, thank you. Another question is why too little cross-care leads to readout errors?
Yeah, so if the separation between the resonator corresponding to 0 state and resonator corresponding to 1 state is not enough, then how would you say that this is 0 or 1? The resonator has a Lorentzian response, like, you know, And then there will be overlap between 0 and 1. If the overlap is big, there is no way to discriminate between the two states. So you got to have enough separation between the resonator corresponding to 0 and the resonator corresponding to 1 in order to have good fidelity, readout fidelity. And of course, this is the starting point. You got to amplify the signal as well. If you don't have quantum amplifier after the resonator, then again, you will not be able to do a single shot measurements. You got to do averaging and so on and so forth.
Okay, I will go for another question about the TE and the TM mode. What's the difference? Yeah, I can read the question.
Yeah, so electromagnetic modes have three main categories. There are other categories as well, but there is TEM, transverse electromagnetic, which means that there will be no EZ or HZ. So if we're propagating in that direction, and this is my XY, and then the Z is the direction of propagation, TEM, transverse electromagnetic, means that there is no contribution for the electric field nor the magnetic field in the Z direction. Transverse electric means that there is no EZ equals 0. Transverse magnetic means that there is no HZ, that HZ is 0. And
okay, because,
yeah, this needs a bit of context, and I invite you to just visit one of the electromagnetic courses. You will find plenty of resources to, I mean, I invite the person who asked the question to read a little bit.
Okay, so I will move forward. How does the inclusion of the quantum amplifier affect the lifetime of a qubit in the QPU?
It does not.
How does the noise scale with the quantum amplifications?
It does not affect the lifetime. So it improves the readout. I mean, instead of seeing a signal and then averaging over time in order to see this discrimination between the 0 and 1 state, you will be able to do a single shot measurements with a quantum amplifier. It does not affect the lifetime of the photon inside the cavity. This is fully dependent on the losses in the quantum chip. Has nothing to do with the quantum amplifier, provided that you have isolation between the two systems, which is the case. There is always isolator or circulator after the qubit and before the quantum amplifier to provide some isolation between the quantum amplifier and the qubit.
Yeah, maybe you can explain a little bit about the principle of operation of the quantum amplifier as an area of Josephson junction, a transmission or resonator.
Yes, so to first order, think about this. So the JJ provide a nonlinearity, and then the nonlinearity allows mixing frequencies between the bump, the idler, and the signal. So you have three frequencies in the system. And then if you meet certain conditions of the relationship between the frequencies, you can end up with the energy moving from the bump to the signal through the three-wave mixing or four-wave mixing and so on and so forth. So this is also quite a bit of a topic to explain alone, but I think I put few resources, few references in the slide that you will find it more entertaining. There is one in Microwave Journal by Amontado. This would be a good starting point to understand the quantum amplification.
Okay, thank you for that. We have maybe the last question. In quantum electronic design software, are we able to simulate other quantum technology instead of superconducting qubits?
So we're starting from superconducting qubits because, as I said, under the hood, they are microwave circuits. And our EDA tools are made for microwave circuits over 40 years of time. So for other technologies like spin, photonics, ion traps, cold atoms, topological qubits, the overlap is less, but there is still opportunities for instance, spin qubits. Can we make laying out the spin qubits more obvious and easier to do? Photonic qubits also. So the short answer that we're thinking about what we can do to enable other quantum hardware technologies in the coming years.
Okay, thank you very much, Dr. Mohammed, for this interesting. But I do have like a last one that is just a curiosity. How does it look like a segment manager at Keysight? How does it look like day-to-day work?
How the role, you mean?
Yeah, your role at Keysight, the segment manager.
Yeah,
just
so
curious.
That's a great question. So it's exciting. Before joining Keysight, I had in mind that there is a bit of a gap between physics and engineering for quantum, and I'm trying to close this gap. And Keysight also, before I joined them, they actually hired me to try to close the gap between engineering and physics, enabling people to design their quantum chips in a more systematic way and enable them to scale number of qubits to tackle better fidelity with quantum amplifiers. So the rule I have is a mix of product management and research and development.
Okay.
Does this answer your question?
Yeah, thank you very much, Dr. Mohammed, for these answers.
Thanks.
And thank you for taking time to answer all these questions and also to attend this workshop with our participants.
Yes.
And
Yes,
we hope
thanks.
we learn a lot from you. Yeah.
Appreciate it. Yeah,
Thank you very much.
pleasure. Thanks.
And
Yeah.
we'll keep in touch.
Bye-bye.
Bye.
Bye.
Okay, now we'll move to the second lecture for today's. Actually, it will be a tutorials by our guest, is Satman Ahmed Shanto. He was already here yesterday. He's one of the main developers of the Squad, which is an open source database of superconducting quantum device design. So we will just continue with him. Shanto, you can take it over. Thanks.
Hi, Alex. Let me share the screen. It's visible, right? Just want to get a confirmation the screen. Okay, awesome.
Yeah,
cool. All right. So hi to everyone who's watching. I hope everyone got the chance to watch the tutorial from yesterday, but if not, again, what we will cover in this tutorial will have the quick message from yesterday anyway, so everyone will be caught up to speed in this tutorial. The idea behind this tutorial is to essentially design a quantum chip that is fabrication ready with squads and Qiskit metal. There's a lot of examples on the internet using Qiskit metal to create chips, but sadly, a good chunk of them are not fab ready. And I feel like this resource would be really helpful because it walks one through how to think about design constraints and design requirements when you're making quantum chips. And it also kind of talks about how to address some practical resource allocation or resource limited design decisions as well. So that's the idea of this tutorial, how to use squads to create a fab ready chip. So for this example, this is the chip design idea that we are trying to implement. And usually this is very typical of how things look like personally in my lab as well. And I think it's typical for most research labs in superconducting quantum devices, where you have an idea, you read some paper or you did some app and you have an idea of what you want your chip to look like, in the sense of, it's Hamiltonian parameters, what it's supposed to be. So in this case, for this demo example, we want a qubit with a target frequency of 3.7 gigahertz and an harmonicity of minus 210 megahertz. And also for this system, we want the resonator frequency to be at twice the qubit frequency. So that's another design requirement. And also, let's say we want to have this, the punch-out shift of the resonator, which as Mohammed kind of covered in the last talk, which again is the shift of the resonator state based on the state of the qubit. We want that to be a little bit high in the sense that it needs to be around like a few megahertz. So we want that as well in our design. And two last things we want is we want to be able to do microwave measurements on this chip in transmission. So it's a 2-port device. And our qubits should have a charge line as well. So let's say this is the design requirement we want for this chip. And this is what I would address in this tutorial on how to do this with squads and Qiskit metal. So let's get started. Okay. Let's load these handy modules. Again, this next 4 cells kind of cover what we did last tutorial. So I'll quickly run over them. We're importing the 2 most relevant modules from squads, the squads database and the analyzer module. And then we make a connection to the squads database. We select our system, which in this case is the cavity claw qubit system. We specify our system, which with the qubit being a transmon cross and the cavity claw being of the rock meander type from Qiskit metal. And we want all our cavities to be a quarter wave resonators. And then we use this create system data frame method to kind of on the back end combine everything nicely together. And then we pass on this database object to the analyzer object. So let's run that. As it's running, since again, based on our design requirements, we wanted a qubit to have this 3.7 gigahertz frequency with an harmonicity of 210 megahertz and the resonator being quarter. We also wanted a big punch-out shift, which there is a formula that we derive. It's in the squads paper, equation 9, but you can use the second order non-rotating wave approximation in the dispersive limit to get G in terms of chi. So you can compute this if you want, but empirically speaking, 100 megahertz coupling strength should give you a pretty decent punch out. So that's how we're choosing this value. And since we wanted the cavity frequency to be twice the qubit frequency, we are computing it based on our requirements. So let's run this cell. And of course, now that we have our desired Hamiltonian parameters ready, we just query the squads database with this find closest method and capture the result in this results variable. So that's it. Everything is ready for us. These are some new methods that I'm introducing in this tutorial. One is this. What's going on over here is from this results data frame, we're capturing the design information for each of the systems in our system or in our combined system over here, which is a qubit, a CPW, and the coupler to the transmission line. So as pretty straightforward method definitions for these things, you just use these methods to get those dictionaries. And since when you're trying to design a chip, you need to know what the LJ, the Josephson inductance, is supposed to be. For that, we have this get LJ's method as well, which would compute the required Josephson inductance for this chip. So let's kind of take a look at what these things look like. So again, these are the design options, are the options dictionary that we would pass on to Qiskit metal. So we have things ready. Let's kind of take a look at what the LJ would look like for this chip. It's this, and note the LJs are in nanohenry here. So cool, we have our stuff ready. Now, this is where the real world kind of kicks in, right? In reality, fabrication is not perfect. It's actually nowhere near it. So what happens is if we only wanted to create a chip with this one particular qubit resonator system, chances are chances are that it might not land exactly where we want it to be. And we would have just wasted our resource in the sense that we just did one unit in our fab run where we could have done multiple to increase the yield and make sure that we have at least one workable device. A device in this case, I'm defining as the qubit cavity pair. So for that, in reality, what we do is we do this concept we call in the lab as spraying and praying. where the idea is that we sort of account for the fabrication uncertainties in the design, and then we spray the parameter sets around it to make sure that we have, again, the highest possible yield for the actual useful device that we want. So let's kind of go over this in this example, what that means. So let's say in our fab run, we can make 4 such devices. So that's what I'm calling here, this num pairs 4. What usually happens, the fabrication parameter that's the most tricky to nail down is the LJ. It is, and the reason why it happens is because the Josephson junctions, as we all know, is at least in most transmon architectures, it is superconductor, insulator, superconductor, which mostly is aluminum, aluminum oxide, aluminum, right? And the LJ kind of depends on the thickness of these 3 sandwiches, really these 3 material sandwiches. But it's very difficult to grow the aluminum oxide layer very precisely. And in this case, we need like angstrom level controls, which again, as you all know, it's a little tricky to kind of nail it down perfectly. But of course, it's done. A lot of foundries do it fairly well, but it is a very tricky thing to do. So for the sake of this example, let's say we can only guarantee our qubit frequency up until 0.75 gigahertz of what we want it to be. This seems a little high, but honestly, it's not very uncommon, especially if the type of fabrication that you're trying to do is the first time that you're trying to do it, and or your fabrication facility is, it's new and you're trying to develop the fab recipe on its own. So it's not unreasonable from experience. So we essentially now need to account for this uncertainty in the qubit frequency into our design. So since we wanted our resonator frequency to land at twice the frequency of the qubit, we need to then kind of create the 4 resonator frequencies such that each of them account for this sort of maximum error that we can get. And that's what I'm doing over here. I'm grabbing the parameter from the target params dictionary that this is the ideal resonator frequency with no uncertainty. And then I'm computing what the worst in the sense that if the qubit is the minus 0.75 gigahertz, if it's lower by minus 0.75 gigahertz, where the resonator needs to be, and if it's the worst in the other direction, where it's higher by 0.75 gigahertz, where does the resonator need to be? So these are the new frequencies or corresponding to that. And since I can place 4 of such systems in my device, I just calculate in a very linear fashion what the 4 resonator frequencies need to be, again, assuming that there's some uniform distribution of this error. Again, if you have if you know your fab process a lot better, then you can tune these sort of spraying to match the error distributions that you get. But in this case, I'm assuming it's just a uniform distribution. Cool. So now that we know what the resonator frequencies need to be for our case, we would want to then scale the length. We know that the coplanar waveguide length is directly proportional to the frequency. So we are scaling we're basically pre-computing the resonator length needed for each of these frequencies here with this linear scaling law. And as you can kind of see, if your target frequency or if your new frequency is higher, this ratio is lower, which means your CPW length is going to be shorter, which makes sense. So we have updated our CPW lengths. Cool. So let's go to the next step in our design workflow to address our fabrication needs. Okay. So another thing is, sure, now that we know the LJ value and we have created this system where even if there's uncertainty in it, we can kind of still have a useful device. Another thing you need to think about is, depending on your fab facility or your foundry, you may or may not be able to just make any arbitrary type of junction. And you may be constrained to only certain sizes of the junction as well. So for the sake of this tutorial, let's say our fab facility would only allow for the Dolan style Josephson junctions, and they can only make those junctions with a fixed length of 200 nanometers. And they would only allow us to vary the junction width in multiples of 10 nanometers, but it needs to be at minimum 100 nanometers. And also very typical, these fab facilities will give you some sort of current densities that they can reliably do. So in this case, they're giving us a choice of either 0.1, 0.25, 1, 0.3 microamps per micrometer squared as current densities. Okay, there's 4. This typo. Cool. So as the designer, it's our decision, or it's our job right now to come up with the Josephson junction area or its dimensions so that our fab facility can actually fabricate this device. So that's what we're going to try to do. So this kind of, since 2 decisions were kind of already made for us, in the sense that they can only do Dolan style junctions and the length is fixed, we only have to answer what the width needs to be and what the current density we're going to be choosing for them to run our job on. So let's recall some fundamental formula for these Josephson inductances. It's inversely proportional to the critical current, and critical current is the JC times the area of the junction. So it's, as you can see, it's pretty obvious from the formula that for a given JC and a given length of the JJ, we can compute back what the given JC, given length of the JJ, and a given LJ, we can compute back what the width needs to be for the junction. So that's what this method is kind of doing. And since we want, for our fictional fab facility, this width needs to be a multiple of 10 nanometers, I'm instantiating this method as well. And right now, what I'm trying to do over here is I'm looping through each of the current densities given to us and computing what the width is going to be for our target LJ corresponding to each of these current densities. So let's see. So this is the result that we find for an LJ of 15.9 nanohenries. If we choose a current density of 0.1, then the JJ width is going to be 1040 nanometers, which is possible because remember they told us the minimum that they can make is 100 nanometers. So this is an option. The second one at 0.25 is 420 nanometers, which also works, also an option. At 1, it is 100 nanometers, which is at the limit of what they want. So this is a little bit risky of an option if we choose to move forward with it. And at 3 microamps per micrometer squared current density, the width is going to be 30 nanometers, which is not an option because it is less than the minimum that they can allow for. So these 3 are viable options, and I'm choosing 0.25 because not ideally, but I think a shorter junction is more useful. Again, empirical evidence for, or not empirical, sorry, it is anecdotal preference, I guess, for me. So I'm choosing this JC for this run, and I'm computing, or I'm recording the width needed for this JC. So that's what this cell is doing. So now we would start to make our design in Qiskit Metal. We import the typical Qiskit Metal libraries needed to make our designs. One note is that I'm going to be importing the transmon cross not from Qiskit Metal, but from squads. And the reason I do that is because squads, it's basic. This transmon cross method from squads is it's a daughter method of the parent method transmon cross in Qiskit Metal, and it has more properties in the sense that you can see in this method, where you can tell it what style of Josephson junction you want, and it would implement that particular geometry for you. So that's why I'm using this method. Over here, I have 1, 2, 3, 4, 5 methods, and each of these methods are taking in various design space variables and creating a component for the design. So this is the create qubit method, as you can see. This is essentially just creating the options variable for Qiskit Metal design, and it's just passing it on. Same thing for the create CPW. It's taking a bunch of design space variables and creating the options dictionary, passing it to the design, passing it to the Q component. Same thing for the coupler, which since we're using a quarter wave resonator, our coupler is coupled line T. And lastly, we have this wire bond method, which is basically defines our port needed for this design. And of course, the feed line, which is the transmission line. So these are the methods we will be using. Let's execute that. Okay, so now we are forced to make another design decision. Since we wanted to make transmission line measurements, already we need 2 ports. Also, since we wanted a drive line on qubit, that means we need 1 extra port for each qubit. And since we are putting 4 qubit cavity systems, there's going to be 4 extra ports needed. So in total, we need 6 ports. So we need to first ensure that we have what is known as a board in our lab. This is just also a coplanar waveguide to connect our chip to the rest of the electronics, the SMA cables, and the rest of our fridge, essentially. So in our lab, this is a picture taken from our lab. We do have a board, so that's great. So we needed to make sure of that. Secondly, another design decision to make is this cutout that we have here is where we will place our chip, right? So we need to make sure our chip will safely and easily fit in this cutout, because if you make it too big, you will be working with the tweezer, right? So there's not going to be a lot of space for you to really move things around, and you might damage the chip. So you don't want to do that. For our lab, this cutout is 5.4 millimeters squared. So we are basically, just to be safe, we're making our chip a standard 5 by 5 millimeters. So that's how we're making the decision. Cool. Another decision we have to make is, again, we need to make 6 ports for our design, right? We need to be able to place them in a way such that the wire bonding to these ports are easy. So in this case, I'll place a port over here. I'll place a port over here, 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 and here, so that I can easily wire bond them onto the, not wire bond, but so what I'm looking for, I'm blanking on the word. But we make single wire connections essentially, and that's what we need to ensure we have space for. And another thing, since we work with readout electronics at the end of the day for our measurements, we need to make sure that everything has a 50 ohm impedance, and which also includes the port sizes. So these wire bond methods with these particular geometry has been simulated and tested to have a 50 ohm impedance. So you can use these numbers. And again, I have put the position such that the proximity of these ports to the traces are ideal for our board. And let's see how it looks like. So great, we can put our connections on each of them, and it looks like how we wanted it to look like. So now we need to add the CPWs and the qubits to our system. And again, I usually start out with making a sketch. Again, I'm clearly not an artist. So this is what I want our chip to look like, the 4 resonators coupled to their qubits with the clock, and each of them would have a drive line. So that's what I'm imagining it to look like. So let's create the geometry for this. And also, one thing to note, I have all the Josephson junctions facing outside, facing the corners of the chip, facing away from the chip or away from the transmission line, so that these Josephson junctions in reality are written in a evaporation step. And this geometry allows me to write all of them in one step. So that's the reason. These are some of the parameters needed to define the parity and the positions of these things, instantiating that. And in this for loop, I am going over the 4 pairs, qubit cavity pairs, and instantiating them. So let's kind of read through what's going on. Again, giving them a name. Each of them will have a name: Q1, CLT1, CPW1. Getting the corresponding JJ width from, which again, we did already pre-compute to be this variable, but also it's always safe to do a max operation on the foundry bin as well, because if you're doing this dynamically, you would always want to make sure that you don't send in a design that has a smaller width than what they can tolerate. And over here in the create qubit method, as we kind of looked at, I'm passing it in all the information that's needed to create the qubit. And as you can see, in particular, all the information coming from this data qubit dictionary are the ones we queried from squads. Similarly, we are creating the CLT objects using this create CLT method. All the information coming from squads, these positions and CLT orientations is what we defined over here, so that my geometry looks like this. And same thing for the CPW. So let's execute it and see what the chip looks like. Awesome. It looks like how I like my sketch, but better at first. But let's zoom in to see if the JJs looked correct or not. Okay, the JJ looks really good, and so does the qubit. However, you can see there's this like sharp kinks in the CPW, which is not good. We don't want this, and this is a known issue with Qiskit metal, really, that it creates these non-rounded kinks in route meanders. And honestly, there's also a very easy fix for it, which again, you can see zoomed in over here. There's a kink here, kink here. You need to just play with the end straight and start straight parameters of the CPW, and empirically, like I found for the designs in this case, these numbers fixed it. Again, these are not unique numbers. You can just play with them and see what fixes it. So let me run this code and see. Nice. Now you can see it's all continuous, so that's nice. And you can also see that all of the CPWs are free from such sharp edges. Perfect. So all we have to do right now is add the drive lines to the qubit. But first, I would like to pause and see if there's any questions in the chat before I move on.
Yes, I can read them for you.
Yeah.
We have one question asking, are there other components from SQUAD also enhanced with additional parameters like transmit cross?
Could you repeat the question one more time? Sorry.
Other components from SQUAD also enhanced with additional parameter like transmit cross.
Oh, yes, we do have some other components, and you can look into the squads.components sublibrary to see what we have. And we keep on adding more and more components to there.
Okay.
Awesome.
Okay, maybe this other one.
Okay, I'll continue.
How does the sorry,
go on. Sorry, I thought there was
okay.
Say that one more time.
Yeah, there's still one question. How does the placement of the reception junction towards the outer side of the chip make possible for the JJ being implemented in the same step?
Right.
What is the process made by? Yeah.
The process is known as shadow evaporation. So the idea is in our lab, in our clean room, essentially what we do is I guess it's typical in every clean rooms really, but you deposit metal. So you have your chip, we have an electron beam gun that we shoot at our crucible, which contains aluminum, and that controllably deposits some amount of metal. And then we can rotate the orientation of our chip and stop the gun, let it oxidize to let the insulator layer grow, and then deposit some material back again. So the process, I guess, to answer the question again, the process is shadow evaporation. And I can post some useful links to read more about them. It's a really cool process. The angle does matter. The angle does matter, because if, let's say, you're not thinking about this, you may deposit more metal on one side than you intended to. So these are decisions you need to make before you even design your chip of how you're going to do your fab process. And again, in reality, let's say we did not do all JJs, or we did not think about this. It's not a big deal, because we can then cover it one side or cover them with resists, or not develop them, and write one half of the chip and do the other. Write one half of the JJs and do the other in subsequent runs. I will move on if there's no more questions.
Okay, we can move on.
Cool. Great question, guys. Awesome. So far we have the qubit cavity pairs, the transmission line, and the ports defined. Now we just need to add the charge lines. As you can see, for this qubit, these three qubits, essentially the charge lines need to come from the bottom. And for this qubit, the charge line needs to come from the top. So that's a distinction we will make. So in Qiskit metal, to add charge lines, we have to define pins first, because if I did not define a pin, the charge line would go straight to the qubit, and that's not what we want. So in this case, we need an open to ground pin. This method is what creates that. Let me kind of give you an intuition of what's going on. What I do is I'm placing a pin at the center position for each qubit, and then center X position for each qubit, and then And then, sorry, I'm grabbing, let me just look over my code. I'm grabbing the positions, the center positions of each qubit's X and Y. And then also calculating or getting from it the cross-link cross-gap, which essentially is this parameter and this parameter. And then depending on whether I want my charge line to come from above or below, I am either, then sorry, I also give it a distance parameter, which kind of dictates how far away from the qubit I want this open to ground pin to be. So that's what's going on. And then, yeah, so that's basically this method. Secondly, once we have the charge lines defined, we need to add, sorry, so once we have the open to ground pins defined, we need to add the charge lines. I found that route anchors is the best component to do so because all the other anchors created 90-degree turns, which we don't want because they cause massive radiation loss and TLS loss. So over here, the logic that I placed for creating these charge lines is, and again, as I don't know if y'all are familiar, but for route anchors, you have to give it some anchored points. Of course, you can manually provide these points, but since I'm doing everything in a more automated fashion, my logic is that I'm placing an anchor at the center position for each qubit, center X position, and the center Y position for each port. So there's going to be an anchor point here, anchor point here, anchor point here, and anchor point here. So I will get nice, smooth charge lines. Cool. So let's execute. Okay, it's already executed. And now the last thing is we need to give it this gap parameter, which I'm defining the gap parameter as the distance away from the charge line, the distance between the qubit and the charge line. This number you have to, again, make it either an educated guess if you've never worked with it, or you can run some simulations in ANSYS. Because if your gap is too short, then your T1 might be really low. So in our case, from data that we have in the lab, 50 microns is decent enough. So I'm executing those methods and voila, that's it. My chip is ready. This chip, one point I did forget to mention is all the other components in this chip also, since we have queried them from squads, are also 50 ohm impedance matched. So this chip is actually fully ready for fabrication from Qiskit Mill at this point. So to kind of also in the spirit of going over the design to fab process, sometimes if you're working with a foundry, they might tell you that, okay, they might tell you to essentially define each component in a different layer. It depends on the foundry really. So for the sake of example, I'm saying that they might want all the metal to be on all the, they might want all the metal layers except for the charge line to be layer 3 and the charge line and the ports to be layer 6. Again, this is a very odd request, but I think it's a good point, a good teaching point to learn how to manipulate these systems. So I'm defining these two variables to encode this information. And next, what I do is I want, again, this is the wire bond for the transmission lines, or the bond paths for the transmission line and the transmission line itself. This is the CPWs, the qubits, the couplers, and the open to ground pins. All of these things, I am basically looping through them in the design.components.items and assigning them this metal layer, because that's what this hypothetical fabrication facility wants us to do. Similarly, I'm assigning the charge line and the bond pads for the charge lines to this charge line layer, which is layer 6. And for it to take effect, you need to do the GUI.rebuild. And now it should have taken into effect. The very last thing you need to do is you need to process the GDS from this GUI or from this design, which these are parameters that we are choosing. So we want to, since it's fabrication ready, we want to set this parameter to true. And again, also more than this, there's a really good tutorial, I believe, on the Qiskit Metal doc side that talks about what each of these parameters in the design.render of GDS means. So I would recommend you all look into that as well. In this case, what I'm basically doing is I'm just telling that, okay, please make all these layers visible in the GDS file. And also since I think Mohammed touched upon this in the last talk, ideally we want to do these air bridges on our system, but again, air bridges are very difficult to make. I've tried making them unsuccessfully a bunch of times. It's very difficult to make. But if your fabrication facility allows for it, absolutely use it. But if it doesn't allow for it, a good alternative is to create these ground plane square holes to make sure that we don't trap flux. So that's what these parameters are doing. And then you kind of define the ground plane holes, like the size of it and how much the keep out areas need to be. There's a paper, I don't remember who it's by, but they do a study they do a study to show what the optimal ground plane square dimensions should be for a given device and how far the keep out regions should be from your coplanar wave from your readout resonators. But I think the idea was as long as it's like greater than like 17 microns or something, it's fine. But I will link to the paper in the inquiries or resources channel later on. But I'm adding those things. And then I use this export to GDS method to create the GDS file. Awesome. Let me show you all what the GDS file looks like.
Maybe in the meantime, I can ask this one question.
Yes, absolutely. Go on.
Yeah, about the layer, like layer 3, layer 6. What do you mean by that? How do we see that?
Okay, that was a great question because I'm just about to answer it. So in the GDS file, I'm using the K-Layout software. It's open source free software. So these are the layers. So as you can see, if I'm not showing the layer 6, everything here is layer 3. So that's what I mean. And if I, let's say, hide the layer 3 and only include layer 6, then the charge lines and the bond pads are layer 6, which is what again, for the sake of this tutorial, is what our facility wanted us to do. And the last layer that I have over here, these are the default layers where I had my JJs defined. This is something you can change in the properties as well. So that's here. So that's what the GDS file looks like. And this is almost fab ready. The reason why I opened it up because I intentionally left some stuff which needs to be corrected for. So over here, where did it go? Yeah, over here, as you can see, this ground plane square is not the same size as the others, right? So, and this is because Qiskit Metal's automatic GDS renderer does create stuff like this, which again is not really a big deal because if you're, let's say, using a electron beam lithography machine to write this device, in the processing software, you can just say that all features less than a certain size in certain layer, just ignore them. So these things will be resolved. But I wanted to intentionally bring this out because this is the type of stuff which might mess up your fabrication run if you're not looking at the GDS file carefully before just running to the clean room. And again, this is also a very easy fix. You can use K-Layout to just merge the layers as well. But it's always a good idea to not fully trust automated software and also trust yourself and look at things. So that's the point I wanted to make. Now, let's go back to the tutorial. Yeah, so as I promised, this was a workflow that my screen is being visible, right?
Yes,
so,
yes.
So as I promised, this tutorial kind of showed how to use squads and Qiskit Metal to create a novel chip that is fab ready. And I hope me walking through this tutorial and thinking out loud about the design requirements and the design decisions was helpful to y'all. Last point, I guess, that I didn't address in this tutorial is another layer if you're working with foundries really, or even your clean room might require it, is there's something known as a design rules check software, or DRC software, where you, before fabricating, you send your GDS file to that software and it will then spit back to you with errors and what are the type of errors there is in your file that might be breaking your fabrication process. So the next natural step after this is to send your GDS file into this DRC software. And after that is when you go to the cleaner. But Yeah, so in the next tutorial tomorrow, I will go over how to use the squads database for machine learning-based interpolation. In particular, I'll show how one can get a bunch of good training data for machine learning models and train. Again, I'm going to do a very simple deep neural net model, train it live with y'all, and then show how the use case of that model is to essentially interpolate on the simulated data that we have in the database to essentially simulate the simulator. But I'll talk more about it in details tomorrow. I'm open for questions.
Okay, thank you, Chantal. We do have some questions, from participants. Is it possible to scale this qubit on squads?
Scale this qubit? Could you clarify what that means?
Actually, there's no more. Maybe, Sapphire, you can clarify your question and then.
Yeah, I've been looking. Yeah, if I don't address anything right now, I look into the Discord server a lot. I will definitely get back to you. Next question.
Yeah. There's a curiosity of the set of device out of squad. As you mentioned, testing in the dilution refrigerator yesterday. How did it turn out?
Oh, someone remembers. I actually could not go to the lab yesterday for various reasons, but it's still cold in the fridge. I did do some spectroscopy measurements over the weekend. Again, I found my qubit and my resonators within 2% of where I expected them to be, which is ridiculous. Very good, ridiculous. And it's a very exciting device. It's not a regular transmon. It's an offset charge sensitive transmons that I'm going to be using to study quasiparticles. So I'm very excited. Actually, I'm going to go to the lab after this talk today. So I will maybe give you guys an update tomorrow.
Yeah, thank you. I do have another curiosity about the GDS5.
Yes.
Is it possible to open the GDS5 with ANSYS and then do some simulation there? Will there be some errors with the frequency if you do again mode simulation? Will there be a difference with the frequency that you get with
Yeah, great question. So yes, ANSYS does allow you to open GDS files within it. I forget if you have to convert the GDS to like a DXF file beforehand or not, but there's a lot of free converters that you can use. But yes, absolutely, you can open a GDS file into ANSYS and run a simulation. But you would have to manually assign materials and your volumes to your GDS file within ANSYS, which again, it's pretty easy to do. And lastly, you were asking about whether there's going to be any difference in the simulation results, right?
Yeah.
So firstly, I'll tell you, it's gonna take forever to run. It's gonna take forever to run, especially if you want any sort of accurate results. You have to have a very fine mesh, which will take forever to run. In my experience, I have found the modular way that we do simulations as described in the squads paper is actually captures the same physics, but runs at, I should quantify this, but extremely fast, much faster than having the entire chip loaded at once, but I should have a better quantification for it. So I would not ever recommend doing the entire chip at once because you need a lot of compute resource to do so. And the only use case that I can think about where that might be relevant is when you have a bunch of features kind of close to each other where you need to account for severe crosstalk. That's when it becomes important. But in a chip like this, the crosstalk is very minimal because I've intentionally spaced them out so that we don't really see hybridization of any states.
Okay. Another question that is maybe a dumb question. If I have the GDS5, is it possible to retrieve, the code that was used to build the GDS?
Yes and no. Yes, I have a code base that does so, and no in the sense that I haven't made it open source yet, but anyone can create it. This will, I think it's in our roadmap for squads. We will make it public at some point, but we do have it.
Okay. Thank you. I think there's no more question for now.